invertible. Remember that?
Okay.
The C has to be invertible in this case. Because y equal to Cx.
Yeah.
So you expect that C is invertible so that it is one-to-one match. Because you need the C as part of that capital F and capital G when you are doing it.
But generally C is a non-square matrix that you schedule.
Right, you can still do it like I showed you with the observer design, like the last time. There the C is not a matrix, invertible. So I did C plus the pseudo inverse. And look at the slides, I think the professor was asking, that's a good question. If you remember the linear thing that I did in the previous, there was a case where we were using the output feedback. And in that output feedback, the C, I was using C, not a square matrix like here. So there, that's why I did that, like different slides, so that you see the different cases. There, the C is a vector. So if we take the C transpose, to make a matrix, and we take a pseudo inverse. So take a look at it. That's why I keep saying that. Go through the slides that have been provided to you. Got it? Yeah. So I think the course does a very good job in terms of, it was planned by both of us. It was so that it has different cases in there. So you can see that what is needed, and so that you need to be complete. Yeah. So take a look at it. Okay. Any other questions before I move on? Okay. So basically that's what we're claiming. Since this is unknown, therefore these dynamics are unknown, and therefore we are using the neural network because we don't have precisely the dynamics, and mainly because of packet losses and delays which are coming out from the network. Okay, so let's go back if no other questions. That is, I'm happy we covered the approximation stuff here. Okay, so then what you do, down here, from here onwards, we are using the reinforcement learning. So if you remember, we are basically writing this error, the residual error or Bellman error. We are taking the V and then we are moving it to the right hand side. This is the temporal difference. You can see that V of y of k plus 1 minus V of y of k. So, and we are equating this equation to an error because since we are using a neural network. So this is k to k plus 1 and this is k plus 1 to infinity. So this is a recursive equation. You see that always you see that. Okay? And so this error is the Bellman error, and ideally, or Hamiltonian, ideally this error should be 0 when it becomes optimal. Got it? It has to be 0 when it becomes optimal. Now, remember that concept we did in high school math, when you are trying to find minima and maxima, what you do, you take the derivative equal to 0, right? Remember that? The same thing. The same thing. So then what you are saying is now we are writing this term here, V and all that, based on these update weights, we are writing that in terms of the actual weights. So this term V minus this will be W hat Vk, difference between the time difference between the bases, between this time and that time, that's given by this delta. The delta gives you the difference. So this is time to go, or cost to go from k to k plus 1, and this term providing you in terms of the weights from k plus 1 to infinity. Okay? Now we need to come up with a weight update law for the critique. We need a weight update law. So now we use the same type of weight update law we call gradient descent. So here W hat of k minus alpha V times this. Now remember I told you this value is always going to be less than 1. Remember A over A square plus 1. And there's a reason we did that, but nonlinear control, if you've taken a course, there was a proof that shows that if you're using normalized, this is called normalized update law. This is mainly to make sure that the convergence and the stability working, okay? But the disadvantage of that update law is that it makes the convergence a little bit slow. So in nonlinear control, people don't like that. So keep this in mind. So, but there are other ways to do it, but it's very difficult. Proofs are very difficult. That's why we have to do that. Now look at that. This update law is driven by the Bellman error. So, and then you know, this EVK, you put that expression and you get that expression, and that's equation number 10. So we know these quantities, and you drive that, and then you are constantly tuning the weights of that critique network. Any questions? Any questions?
So, if you tell about the gradient descent.
Okay, so the gradient descent, what it means is it's like a hill, right? Let me see, okay. So let's say hill. So you have a hill, and you really want to come to the bottom of the hill. That's where you really want to converge. And you are somewhere here. And normally we teach this in neural networks and other stuff. So you start here. There are two things that makes in order to reach this. Okay, what are the two things? One is how big is the step you take. Okay, how big is the step, right? The second is the direction of travel. You can go in the opposite direction. If you are taking the opposite direction, can you reach the bottom of the hill? No. Okay, so in order to do that, it's also equally important how big is the step size. Why is that? Let's say you reach here and your step size is big. So what will happen? Once you reach here, instead of reaching to this point, you may just go to here. And then you want to reach here, then you go back here. So how do we know that we take the gradient, the derivative, and the derivative becomes negative? That means you are decreasing. And then if you switch to the other side, it becomes positive. Then you know that you overshoot that. So that's why it's called gradient based. You take the derivative, so you take a cost function, e square or something, and then you take partial e square over partial w. That's what that operation is called gradient. And it assumes like you're going down with a minus sign. It has to decrease. That's a very simple explanation and that's why you get a minus sign there. Okay? And you have a constant, it's proportional to the gradient. You put the constant is alpha v, which is the learning rate. And the learning rate is the size of the step. How big is your step you are taking? You see what I'm saying? Any other questions?
Sir, in case of in case of optimization, gradient based method, so in that case the update is that xk plus 1 is what you have written, xk plus 1, xk minus that alpha into, but derivative of the fx,
right.
F of function of x.
Right.
Here the
E square. Here is the Bellman square. So you're trying to minimize the Bellman square. So what you do is you take half.
And this is Bellman square and then half.
Yeah, half of that. Yeah, then you take the gradient of it. Because you want to minimize that Bellman error to 0. Fair enough? So it has meaning behind it. That's what I'm skipping it because I don't know whether we'll have time. So any questions? I think that was a very good question. I didn't cover this because some of you don't have the background. And so it probably, it takes a long time, but this is a very simple explanation. The more details are there in the paper that Prasad has sent you. Look at that paper, it gives you. But as I said, you've got to have a neural network class to understand, like optimization. This is all typically covered. Like what is a gradient descent, yeah. And you always take a quadratic function, you take the derivative with respect to the weights, that's why you're getting that equation there. And the goal is that you want to minimize it and you reach the bottom of that hill. Okay? Any other questions? Any other questions? Okay. So remember I said there are so many courses is included here, and it's not possible to cover all of them in that short 2 weeks. We were thinking maybe we should add in 1 week today, but 1 week would have been even worse. Yeah, so maybe it's 2 weeks is kind of an idea. Yeah. As long as there is some happiness from you guys thinking that it's what I know many of you came leaving the classes, right? So I think, yeah, that's 2 weeks is a long time if you are missing classes. So, okay? All right. Any other questions here before I go? Next slide. No. All right. So the same thing we do for actor design. So the actor design, that's the next thing. We did the critique. So the actor design is basically you're approximating it by the one single neural network, and that's because you need the G. You need the capital G in this case, and since we don't know it, so therefore we are approximating it, and we need to find a way to tune these weights of the actor. And so you see that since we don't have the G, we are replacing that G by the G hat from the identifier. So we are computing the optimal control input by 2 different ways, and we are subtracting it because they are both supposed to be equal. And since we don't have any measured quantity, this is the best way to show. So this is the output of that minus of that is basically what we call control input error. So this term is called control input error. Okay, control input error. So this is the measured quantity. So we use this quantity to tune the weights of the actor. And we use the same gradient descent. Okay? So now, with this we can show the proof. The proof is in the paper. And so, via Lyapunov method, performed UUB. Remember I said UUB can be obtained, identifier, everything. And I think in the proof, I want to show you a little bit in the proof. Since we have not covered, I have this slide. And you see that you need to first select the initial controller to be admissible. And, you can pick here stabilizing control policy. I would basically make it admissible. So this should be admissible control policy. You use these weight update laws. And these are the constants. And you claim that identification error, output error, weight estimation errors of the critique, actor, everything is UUB, and look at the Lyapunov function. So Lyapunov function is a quadratic in the output, and identification error, okay? So there is an identification error, there is the value function weight estimation error, Bellman error, then you have the critique error, and this is the identification. So everything is included here. And then what do? You take the first difference. In continuous time, we take the derivative of the Lyapunov function. In discrete time, you take the first difference. Okay? And then you manipulate everything and you show that delta V is less than, okay? You see that you have some positive constant times k square. Sir, you see this K? Yeah. You can't miss it. You can't miss it. So here is the learning rates. This is how Sir also was showing you last class that how the learning rates are, there are some bounds. Remember that in the paper? So those are, we use those because we need that delta L has to be less than or equal to 0 for our, so therefore we show that K has to be less than half, all that alpha C square has to be less than 1 because this has to be positive with a minus sign. This is always positive, therefore with the minus sign this is always negative. And that shows that we are decreasing, delta L is decreasing. So all this stuff comes out of the math and you get a constant. This constant is all the approximation errors. And from there, see if this constant is 0, most likely you can show asymptotically stable. Since this in the mean square, since this constant is non-zero, we can only show boundedness to the mean. Okay? Any questions here? Any questions? The one before? Yeah. So yeah, LDN is basically error in the output. We just gave a name, you know. LUN is the weight estimation error of the control. LVN is the weight estimation error of the value function neural network. LCN is basically the error for the, I think this is the identification my gut feeling is, okay? So you see that this error is the critique weights. So this is basically combination of those two. Yeah, I don't know, maybe let's see here. What is that, what is the identification error? We use some identification. CK, yeah, that's identification. You see? So basically we have to include everything. And you have to make it a quadratic, and then you are showing that everything is bounded. The whole closed loop system is bounded. Okay? Any other questions, guys? Any other questions? So you see that how the bounds come in, and I showed you why it is UUV, not 0, okay? So any questions? So we are not showing anywhere any other math equation. So I won't show you any more proofs. This is the last one I'm going to show you because we won't have time to show you. But remember, I only showed you the last step. The details of the proof is in the book or, or in the papers. Papers sometimes may not have a little more details. The book might have a little more details. Okay? Any other questions? Okay, so let's see if this makes sense. So here are the bounds. From there, I was showing that the error in the output is bounded, the identifier weights are bounded, the value function weights are bounded, the control input neural network weights are bounded, and the output is bounded. So all this is bounded, and basically we show that it's bounded in the mean, so basically everything is bounded. So here is a flowchart. And there are two flowcharts. On the left-hand side is the HTTP VI. Here is an offline process. You do the control policy. You start with some initial value. And then you have the control policy update, control input error, value function using least squares, and then you compare it. And then if it's not, I equal to I plus 1. So here you are making k equal to 0 or k equal to 1. And then you do that, you iterate it. Once you iterate it and this happens, then as you're coming out here, if it's yes, then you have another loop, k equal to k plus 1. And then that loop goes back here. Okay? So 1 is the time, k is the time, I is the iteration. So remember I told you, you hold the time in a sampling interval, you iterate it till it converges. Then once it converges, then you increment the time, k equal to k plus 1. And then again you go back and do the iterations. Within the sampling instant. That's right, that's what I show you. That's the drawback. Remember I showed you what happens when you can do that, because nobody can tell you how many iterations you need within a sampling interval. And that depends on the nonlinear system. There are so many different factors. No, same. Yeah. Same. So this is on the other hand, look at this second flow chart. This is the current flow chart that we derived. You initialize it, you initialize the control input to an admissible control input. You first define the identifier. Then you define the update loss for the identifier. Then you are looking at the value function, critique update law. Then you are looking at the control input, which is the action network, and the actual control policy. And then the control input error to tune the weights. And then here there's no iteration. So k becomes k plus 1 and you keep going back. You see? Any other questions here? Any other questions? Okay. So here is an example. So this is an example of a nonlinear system. It's an affine system, y equal to cx. You see c is known, and maybe this is invertible, probably. 2 minus 1 is 1, yeah. That's invertible. So here is an f of x, this is g of x. We updated it with all the packet losses and everything, and you end up in getting this is f, this is g. And here is the history. So sampling interval is ts equal to 0.1 second. The delay bound is 2, random delay, E of tau is this. Bernoulli distribution with E equal to 0.1. Here identifier, critique and action updated at each sampling interval, like I said. So now we started with HDP, the heuristic dynamic programming value iteration. Now look at that. If I'm using 100 samples, 100 iterations per sampling instant, nicely stuff converges. Okay? Now what happens when I'm using 10? What happens here? It blows up. Okay? And it blows up because in the numerical iterations, it's not converged. So if you stop the numerical iterations halfway through, instead of converging, it blows up. It's not even bounded. Okay? Now, so the next step is the effect of delays and packet losses. So here, we are implementing a stable controller. We found a stable controller from this, my paper. Okay? And here we don't, that controller doesn't know the delays and packet losses. It's an affine controller. For an affine system, continuous time, it doesn't know the delays and packet losses. So I try to see whether what will happen. What happened here? What happened here? It blows up. So what does it tell us? It tells us that delays and packet losses can cause instability, even though that particular controller is able to stabilize it, the nonlinear system, without delays and packet losses. You understand the difference now? So we are taking one at a time, and we are trying to show that. Okay? So now if I know the wireless imperfections, and if I don't, since I don't know, now I'm using, in figure 9, now we are using our method we developed, and nicely shows that it converges perfectly. Okay? So what we are claiming is wireless imperfections affect the system stability. Okay? And we also plotted the critique action neural network weights, and you can see after a few seconds, basically these weights converge, the control input converges, and like I told you, initially, okay, so initially there is a slight overshoot observed at the beginning of the figure, and it's due to the initial online learning needed to tune the critique action network and optimal control. So that's why you see there is a spike while the neural network is trying to figure out. So since we are initializing it to 0 or some random value, it's basically trying to learn, right? Remember that. And that's why you see a spike and quickly learns it. Once it learns it, then things get pretty good, right? It converges. Okay? Here is the flowchart. The same thing we did, control input, update loss for the identifier, the Bellman error, residual error, critique update law, and then goes back. Okay? Another example. This is a different example. Here, look at that C matrix. The C matrix is different, right? You saw that? And this is invertible. C is not invertible? Yeah, it is invertible, right? So C is invertible. This is a different system. And here the TS sampling time is 100 milliseconds. Delay bound is set as 2. D bar is 2. Mean random delay values are 80 milliseconds. E tau is 150 milliseconds. This is sensor to controller. This is controller to the actuator. And packet losses follow a Bernoulli distribution, P equal to 0.3. And to update the ergodic behavior, always we are doing Monte Carlo, 1000 iterations. Don't forget that. We do the Monte Carlo and we average them out. Goes without saying, because all this is stochastic. Okay? So, the augmented state vector, remember we talked about it, since output is alone is measured, yk, see that? So here is yk, and then the augmented state we are taking uk minus 1, uk minus 2. So the dimension of this vector is 3 by 1. And we are using tangent hyperbolic and a polynomial activation function. Okay, and here the critique uses 6th order polynomial. Okay, and it was generated using the gradient of the critique. And here is the alpha C, alpha V, alpha U. Okay, simulation was run for 20 seconds. And first 10 seconds, exploration noise was mean 0 variance. This is mainly to create persistency of excitation. Okay, so performance of the static feedback controller, static. And then if I'm using static controller, it can stabilize it without packet losses and delays. The minute I use the packet losses in the system, things blow up. Here is the stochastic controller. Using our approach, it converges, the critique parameters converge, the control input converges. Okay. And you can see that this is the heuristic. So I want to show you the heuristic. So we use the HTP. The HTP would converge when we are using 100 times per sample. It blows up when 10 times per sample. Okay? So that's your conclusion. I think that's my last slide. Any questions here? This is infinite horizon. Any questions?
So if the C is not inverted,
Huh?
if the C is not inverted,
Then you can do it. You can use it. You have to take that pseudo inverse. You could use the pseudo inverse, but I'm just saying that you have to have the C that is inverted. Well, you cannot, because it's not observable. You cannot use it. So you have to meet the observability criteria to use that. That's where that C is going to play a role, right? Remember I said if it's not observable, you can actually modify the location so you get a C matrix. Yeah. That's right. Okay, any other questions, guys? Any other questions?
Sir, invertibility of the C's, why it is required? In that case, if you are using pseudo inverse, so in that case,
so pseudo inverse is not always, you probably know there's a left and the right. So there are reasons why, if you can get a pure invertibility, it's good. But you don't need the invertibility, you can use still the pseudo inverse. But what happens is we have seen in some cases, it's a problem. In some examples, it caused some problem. That's why I said. But you can get away with pseudo inverse.
no, the purpose is to get X from the Y.
Right. That's where you need. Nowhere else. And also, when you build that capital F and G, you also probably need that C. Sometimes, that's another way, another place. So that's why I think it's an issue. What other questions? Any other questions, guys? All right, I think we may stop for tea. And that will give you what I thought. I don't know whether you were here. I brought my laptop, so I wanted to show you. We will not record this because I'm going ahead by one lecture. I thought today there will be more students, but it looks like there are fewer. We will do the same thing maybe at the end, if at all. So I'll play some videos, I don't know whether I have all of them that I want to show you, but I'll try. I thought I would put everything in a folder and like you were asking the localization as well. Yeah, but I'll show you the autonomy part and we'll see if it's not there, then I'll try to, maybe on a different day we can bring that, okay? Yeah, we'll stop it, we don't need recording anymore. Thank you.